In order to successfully make your oscillating chemical reaction, we need to take a little bit of time to review some things from our past. Your notes packet on page 5 offers a nice review of the mole and molarity. So turn to page 5 of your notes and let's look back at some things we've learned in the past. You probably noticed that your recipe for the oscillating reaction requires you to use the concept of molarity to figure out how to mix your solutions to be successful. To understand molarity, we have to go back and remember learning about the mole long ago. We've used this in a lot of get it together problems, so it's probably still pretty much fresh in your brain. Remember that when we work with the mole, we had a sentence that helped us, and it said, use the periodic table and add all the numbers together to get the number of grams that is equal to 6.022 times 10 to the 23rd, either atoms, molecules, or formula units, depending on whether you had an element, a molecular compound, or an ionic compound. And that was equal to 1 mole of whatever the chemical formula was. And we could make this little sentence for any compound, and then from this little sentence, we were able to calculate how many moles were present. Our example problem here asks us how many moles are in 23.7 grams of CuSO4.5H2O. Notice that this situation is similar to the oscillating reaction when you have to work with the MnSO4.2H2O. This little .H2O that's present in a lot of chemical compounds is something called the water of hydration. You probably remember from making your snow globe a few days ago that when these crystals form, crystals often form in the presence of water. There are some chemical compounds that when they form into crystals in the presence of water, water molecules get trapped in the crystal structure and essentially add to the molar mass. The water of hydration doesn't really change anything when you're making calculations other than it needs to be added in as part of the molar mass. So when we calculate the molar mass for CuSO4.5H2O, we have to do the mass of a copper, plus the mass of a sulfur, plus the mass of 4 oxygens, plus the mass of 10 hydrogens, plus the mass of 5 more oxygens. If you take the time with your periodic table to add up all these parts and pieces, you find out that the molar mass for CuSO4.5H2O is 249.6796 grams per mole. The only thing the water did here was make the molar mass a little bit bigger. You'll have to be aware of this when calculating the amount of MnSO4.2H2O to put into your oscillating reaction. Just remember that the .2H2O simply adds a little bit of extra to the molar mass. Our plan then is to go from grams of CuSO4.5H2O to moles. And we're quite familiar with this procedure. We take our 23.7 grams of the copper 2 sulfate pentahydrate, we multiply by 1 mole divided by the number of grams in a mole, and we find out that 23.7 grams of the copper sulfate pentahydrate is 0.0949 moles. Now we're going to take that concept and tie it to another old concept, that being molarity. You probably remember that molarity is abbreviated with a capital M and is moles of solute per liter of solution, or we often simply abbreviate this moles per liter. Our example problem here asks us to find the molarity of a potassium nitrate solution obtained by dissolving 1.53 grams of KNO3 in 250 milliliters of solution. So we need to find the molarity, but we know that molarity is moles per liter, and we are given grams and milliliters. That means we're going to have to start by making a few conversions. We need the molar mass of potassium nitrate, which we can get by adding up potassium, nitrogen, and 3 oxygens from our periodic table, and we need to remember that there are 1,000 milliliters in a liter. Our plan here is ultimately going to be to do molarity as moles per liter. And our solve step we first need to convert grams of potassium nitrate to moles, and we need to convert our 250 milliliters into liters. So we use the conversion factors we found above to make these conversions. Once we know how many moles of potassium nitrate we have and how many liters we have, we can simply take our moles, divide by our liters, and calculate the molarity of the potassium nitrate. At this point, you should pause the video and complete the first 3 practice problems in your units of concentration practice problem set. As you complete these first 3 problems, I want you to remember that in our molarity equation of molarity is equal to moles per liter, you will typically be given enough information to get 2 of these 3 pieces, and you have to solve for the 3rd piece. The first 3 problems represent solving for each one of these pieces, so be sure to focus on your molarity equation and just think about what piece it is that you're missing. After you've completed the first 3 problems, please return to the video, and the video will show you how to calculate the concentration of the ions, which you'll need to do for question number 4. Welcome back. Hopefully you successfully solved the first 3 problems of your concentration practice problems. The last idea that goes with molarity is one that we really haven't dealt with before, and that is the idea of finding the concentration of the ions. Most of the time, we're looking for the concentration of the entire chemical compound. But if we wanted to talk about conductivity, which is dependent upon the number of ions present, we'd have to look at how many ions were present instead of how many formula units were present. To do this, we have to remember that ionic compounds, when dissolved in water, fall apart to form ions. In the case of potassium nitrate, it forms potassium positive ions and nitrate negative ions. Looking at this chemical equation, you can see that 1 formula unit of potassium nitrate falls apart to form 2 ions. And that would equate to 1 mole of potassium nitrate being equivalent to 2 moles of ions. To figure out the concentration of the ions, I'm going to take the concentration that I had calculated before for the potassium nitrate, and remember what molarity means. Molarity simply means that we have 0.0604 moles of KNO3 per 1 liter of solution. Knowing then that I have 2 moles of ions per mole of potassium nitrate, I can use my dimensional analysis, cancel out my moles of potassium nitrate, leaving me with moles of ions per liter of solution, or my molarity of my ions. That brings this video to completion. You should now be able to go back to your concentration practice problems and complete problem number 4.